Hello everyone, my name is Shaowu. Today I want to talk about my latest work, Neural Implicit Flow, a mesh-agnostic representation learning paradigm for parametric spatial-temporal field. Fluid dynamics is a very exciting field. So here you see is a flow visualization of the wake flow coming from an oil passing through the wind. So here you see many small illuminating particles. These are actually the representation for high dimensionality in fluid dynamics. If we view fluid dynamics as some kind of dynamical systems, we will end up with a nonlinear dynamical system like this. Because you can see there are so many illuminating particles over there, this system would end up with a really high dimensionalities, like for example, around 10 million. So it actually induces many problems like predictions, controls, uncertainty quantification in a very efficient way, because we cannot really afford solving those high-dimensional nonlinear systems using traditional methods many times. But if you're looking at these parameters, you're looking at these particles, you see those particles, although there are so many of them, but they seem to obey some low-dimensional structures. Therefore, it induced the idea of can we find low-dimensional latent representation, x hat, maybe just 10 dimensions, but it is good enough to preserve the dynamical behaviors in high dimensions. Okay, so this is the task of this is called dimensionality reduction in fluid dynamics. So mainly there's two algorithms out there. The first one is pop orthogonal decomposition. So basically you have a super long vector. You basically get it by flattening all the variables on a mesh. Then you're stacking them over time. Once you're stacking them over time, you perform a singular value decomposition. The V transpose matrix that you're getting, U as V transpose. The V transpose is the latent representation. The second family of methods is called convolutional neural networks. So basically you downplay fluid mechanics as images. You do some uniform pixelization. Once you do that, you can perform a standard convolutional autoencoder, and you're getting this latent representation right here as a small pencil over here. Dimensionality reduction has really profound impact in our community. For the past 2 decades, this is another complete list. I would say it's a pretty incomplete list of all the beautiful tools that we have developed in our community. All of them rely on dimensionality reduction from either one of these two methods. Okay. However, in the real world, the data set is pretty complex. The first example I want to tell you is about a depth and mesh refinement. So this is a picture I stolen from a Boeing point from Boeing company. So as you can see here, you see there are many, the mesh is pretty refined near the vorticities, where the vorticity is pretty high. Okay, so when the flow goes by, the mesh will change at every time step. Therefore, the flow topology the mesh topology will change, and the number of mesh points will change as well. Therefore, at this situation, you cannot use POD because you cannot stack them like a fixed length vector one by one. In the second situations, here's a supersonic inlet. So basically, when you're changing the parameters, things like pressure ratios, because the shock wave location changes a little bit. So you will need to refine the mesh and changing the mesh a little bit to make sure it captures the shock wave physics very well. For those cases, you would also meet the problem like you cannot, the mesh won't be the same for different parameters. So you won't have a single fixed mesh for all time and parameters. So you cannot use POD. How about CNN? So CNN is suitable for image classification. So think about these cat and dog problems. Okay, fine details are really not that necessary. Actually, what you need is perhaps very coarse information. So for example, if I'm crossing the image a little bit, you can still tell it's a dog, by the outline of the airs here, maybe. You can still tell it's actually a cat, maybe because the air here, or maybe because eye colors. You know that dot won't have these eye colors. Okay, so for those tasks like image classification, critical information is stored at a very coarse level. Therefore, CNN is a suitable choice. However, CNN is not optimal for fluid mechanics. So here I'm going to show you an example of shock turbulent boundary layer interactions, where shock waves is going from here and is having impingement with the boundary layer right over there, and it will reflecting back upwards. You can see here that there are so many small structures right here near the wall, but above the wall there's only large shock wave structures. In those cases, as you can see, a uniform pixelization is definitely a wasting of resources. Okay. So there's actually a second reason for why CNN is not optimal for fluid dynamics. I'm going to give you a quiz on this. Well, what do you think? How much GPU memory do you need for a 64 cubic inputs in a 3D UNet with a batch size of 16? The answer is 10 gigabyte. You may think, oh, okay, maybe it's still affordable, but 64 cubics is the state-of-the-art 40 years ago in fluid dynamics. And if you want to do any kind of serious challenging turbulence studies, you definitely want to go beyond the 64 cubic. And in 2D CNN, the memory actually scales quadratically, but in 3D CNN, it scales cubically. This is why CNN is not optimal for fluid dynamics, especially if you want to do serious 3D fluid dynamics problem, like, for example, turbulence. Okay, so now I'm going to providing my solution to this. It's a framework called neural implicit flow. So neural implicit flow contains of two networks. The first one is ShapeNet. ShapeNet takes spatial inputs XYZ and outputs the quantity at that location. And the other net is called parameter net. The parameter net takes external factors other than spatial. Anything else is put in here. Okay, you have time parameters like Reynolds number, sensor values, you put them in parameter net. Okay, so then the parameter net the output of the parameter net is the weights and bias of the shape net. In between, there's a bottleneck layer over there, which representing the, basically this is a latent representation. From the latent representation to the weights and bias of the shape net, it's a single linear layer. Okay. So you can see now that the neural implicit flow is only taking pointwise as an input. Therefore, it can naturally extend it can naturally apply to adaptive mesh refinement data set. Okay, so the first thing I want to note is spatial complexity here is actually decoupled away from parametric and temporal complexity. The reason why is because we query space much more than time and parameters. So in this way, we can have a lot of saving in terms of computational resources, because we can actually design a pretty small shape net, but complex parameter net. In this way, we can query the flow field really, really fast. Moreover, by decoupling spatial complexity away from other parametric or temporal complexity is in the same vein of traditional low-dimensional manifold model order reduction sort of the philosophy. Because in those places, we also only reduce the spatial complexity other than reducing parametric or temporal complexity. Okay, so it's better and easier for you to extending existing methods that develop from those frameworks in the context of neural implicit flow. Okay, the second one I want to talk about is the ShapeNet is actually, there's nothing magical about ShapeNet. It's just simple dense layers or assignment layers. This is actually the same thing for parameter net as well. So they are not very fancy, they didn't have really fancy structures. The third one I want to mention is regardless of the ShapeNet, the weight and bias of the, regardless of the parameter net, the weight and bias of the shape net lies in a low-rank linear subspace, where the codes, or you can say the latent representation in this subspace, is determined by the input to the parameter net. Okay, that means that just means from the latent representation to the weights and bias, you can just imagine they are just like coordinates in a linear subspace. Okay. So the take-home message is new implicit flow is a mesh-agnostic nonlinear dimensionality reduction framework. And the model complexity only scale with intrinsic complexity. It doesn't scale with the superficial complexity, like how many grid points you have, because you see it's because it's pointwise. So it's not directly appeared in anywhere of the model process. Perhaps you're getting more training data. Okay, so now I'm going to show you some applications here. The first application I want to show is an autoencoder for adaptive mesh refinement. So we're starting with this problem. This is a very famous Rayleigh-Taylor instability problems where you have heavy fleas above, lighter fleas below, and basically the interface will have instabilities and will have beautiful mushrooms phenomena. So as you can see, this is the result when you apply POD, and here's the result when you apply CNN with different resolutions, basically different levels of pre-processing for your data set, and the last one is NIF. So if we have a zoom in on this, you will see that the NIF actually performed the best compared to other frameworks, and the POD performs the worst. And CNN's performance will only improve when you increasing the resolution. Basically, you need to having a finer and finer pixelization. Okay. So if we draw the plot of reconstruction and testing error versus the number of ranks that you use in the latent space, you can see NIF, the black line here, outperform other methods. Okay, this is great. The next application I want to show is a mesh-agnostic data fit surrogate model. So the idea is very simple, is that basically you're going to generating several spatial-temporal data set coming from numerical solvers, which basically you're just changing parameters for the solver and you're getting the data set. Now you want to create a model. Let's say you're getting this model, you want to be able to predict the dynamics on different unseen parameters. So in this problem, we choose the 1D parametric common model Steve-Sinski problem. And then we're just generating the data set and we fit it into NIF right over there, and then we're testing the unseen parameters. So it's all about generalizations. The first thing coming up in our mind is that we want to compare against a vanilla sort of implementation. So basically, how about put spatial coordinates together with time and parameters mu into a single network, and then this is still trainable, right? Now let's see how it goes. So so here, these x-axis here is basically telling you how many training points in the data, and the y-axis is basically the testing error. The lower the better. As you can see, the blue line NIF performs better than the sort of MLP, the naive implementation, when you changing the size of training data. For the second figure here, still the y-axis didn't change. The axis is becoming the model capacity, so the number of trainable models, number of trainable parameters in your model. So you can see the blue line, the NIF also outperforms the MLP right over there. Great. Okay, so the next application I want to tell you about is DMD, dynamic mode decomposition on adaptive mesh refinement data. So for this is a very classic problem, flow of a cylinder. And what's different is that now the data actually coming from adaptive mesh refinement solver called Pele. So as you can see here, there are mesh refinement near the vorticities, and actually those refined mesh will chasing the vorticities. So the mesh topology will change over time, and the number of mesh points will also change over time. So you cannot straightforwardly apply POD. Okay, so in these cases here, we modify the NIF structure a little bit. Instead of using the parameter net to fit the entire shape net, I'm going to use a parameter net to only connecting to the last layer of shape net. Okay, every single layer before last layer in the shape net will be freely trainable model parameters. Okay. So then we train this network. Once we train this network here, we were extracting out the parameter net, and we're just evaluating the by feeding different time t over there. Then you can get in the so-called latent representations for this case. Basically here there are 10 beautiful curves over there. Then you can apply dynamic mode decomposition on these 10 different curves. with the help of spatial basis, you can back out what the eigenfunction is and the eigenvalues for the problem. So now you accomplish dynamic mode decomposition on adaptive mesh refinement. So the message I want to tell you is you can actually extending this type of ideas on sort of extending existing POD-based framework to heterogeneous mesh data set. Okay, so the next thing I want to talk about is compressed representation of 3D turbulent flows. So the task is actually pretty simple. Let's say you have a 20 snapshot of homogeneous isentropic turbulence. Now the goal is to say, hey, how about training the NIF architectures on those data set, and basically you perform a kind of a compressions. Okay, so let's see how it works. So here is a U velocity profile. As you can see, the ground truth here, NIF is over there. It matches pretty well. And I want to do a little bit further. How about comparing the Q criterion and the vorticity, because they are high order quantities, so they'll be more challenging to reconstruct. So as you can see, here is here is the ground truth. This is the predictions. They also matches pretty well. Okay, good. So now, in these cases, I want to tell you that actually, at the end of the day, we actually achieved almost 1,000 times compression. So what I mean by that is, when you're training this data set, you basically end up with this model. Then the model size is actually not as large. It's actually 1,000 times smaller than this data set, right over there. Okay, and we haven't done any sort of tunings, which we will be doing in the future, so we can cut it even more. Okay, good. So the final example I want to talk about is data-driven sparse sensing. So the traditional sparse sensing algorithm is called POD-QDIME. So basically the idea is I'm going to give you the freedom to choose whatever sensor you want to put in a spatial-temporal field. And given those sensor measurements, I want you to tell me what exactly the spatial field should be given those sensor measurements. So this is a sparse sensing problem. And so here we use POD-QDIME to select where the best sensor location is. Once we're getting those best sensor location, we take the measurements and we can feed them basically into a parameter net right over there. Okay, so here the problem we're choosing is a sea surface temperature prediction problem. We take 16 years sea surface temperature data as training data and testing for the next 15 years. And this data set is actually a little bit chaotic, so it's not an easy task actually. And so here I want to show you the results right over there. So here the first plot you see is the traditional method, POD-QDIME. So the solid line here is basically the training error and corresponding to the training error. The x-axis corresponding to the number of sensors. So the y-axis corresponding to the errors. So as the number of sensors increases, the training error of course decrease because getting more information. But the testing error actually goes way large after 5 sensors. This is a very interesting phenomenon. And so how about these traditional methods comparing with NIF? So it's on this figure. Okay, in terms of training error, it's right here in this figure. As you can see, the blue line NIF converge much faster than traditional POD-QDIME. And in terms of the testing error, basically it's the zooming, the kind of rescale figure is right here. As you can see, the blue line of the NIF outperforms the traditional methods, which is the red lines over there, outperform the best performance of the traditional method after 200 sensors. Okay, so this is good. So as a summary, NIF-based frameworks outperform the state-of-the-art methods on data-fit mesh-agnostic models, data-driven sparse sensing, learning latent representation of high-dimensional data from arbitrary complex structures without necessary loss. Okay, another thing I want to mention is that NIF, the key idea of NIF is that it isolates spatial complexity, such like multi-scale, away from temporal, like chaos, and parametric complexity, for example, like bifurcation, to achieve sort of flops and memory advantages when querying in space very frequently. And also this follows the same idea of previous traditional reducer models where dimensionality reduction is only happening in spatial direction. In terms of a more broader view of where we are, I want to give you picture of it. So here is where we are. Perhaps the z-axis is low-dimensional manifold method, and this axis is spatial sort of methods following spatial invariance, and this y-axis is the physically informed neural network. So you can sort of call these are the sort of coordinate for reducible models, for data-driven modeling, for partial differential equation systems. So we're basically right over here, as you can see. We're basically between the axis of low-dimensional manifold methods and the phasing informed neural network. Thank you for listening to my talk, and thank you very much.